Hi guys, today's lesson, the first physics lesson, is 2.1 and it's on prerequisite skills. So these are skills that you need in all of physics to be successful. So we're going to spend some time on some of the basics. The first slide in your notes is on graphing. Those of you who registered for Physics 20 and Science 20, but more specifically Physics 20, you will need to analyze graphs quite a bit in that course. I don't recommend that you skip over this slide, even though we're going to skip it for COVID. But if you have questions about proper graphing and how to read a graph, and you've enrolled in Physics 20, please ask me. We are going to skip over it for this though. First skill that you need in physics and in chem, but we didn't give you any metric conversions in chem, is converting from, say, grams to kilograms, or meters, kilometers to meters, something like that. So what I like to remember is King Henry drank my dark chocolate milk. There was a poster on my wall about this. We looked at it in the measurement unit of math. And this is going to convert all of your metric conversions. So like meters, liters, grams, that kind of stuff. So what this tells you is the middle M, this is where your meters are, or your grams, or your liters, okay? And the first letter of each word is your prefix. So like the king, the K would mean like kilometers. The C down here would mean centimeters. Okay, and what this does is it tells us how many decimal places we need to move. If I start with something in kilometers and I want to get it into meters, I would move from the K to the H to the D to the M. Those little loop-de-loo things I just drew, those are your decimal moving places. So your decimal would move 1, 2, 3 places to the right. So this tells you how many decimal places to move and what direction to move them. Now, some of the common physics units that we use are meters, seconds, and kilograms. This is different than chemistry. If you take multiple sciences, you're going to need to know the common units for chemistry. Chemistry uses grams, not kilograms, so you need to wrap your head around the difference. Now, let's do an example of a metric conversion here. Let's say I gave you 12.4 centimeters. I want you to convert that into our base unit in physics, which is meters. So back up here at King Henry drank my dark chocolate milk, I'm going to go from centimeters to meters. And you have to remember that meters is the middle one. This far M on the right stands for millimeters. So centimeters is where I'm starting. 1, 2 to the left. Here's my decimal. 1, 2 to the left. My decimal is now in front of the 1, so that'd be like the number 0.124 meters. Now, if you've learned to divide stuff by 1,000 or times by 100, or you've learned a staircase to change, that's all fine. You have learned metric conversions before. You should be able to do them. Pick your method. This is the one I prefer, and be able to change metric conversions flawlessly. Now, time conversions. There's some stuff that we just assume is common sense. Time is one of them. So we assume that everybody knows some of the common things, like 1 minute has 60 seconds, 1 hour has 60 minutes, 1 day has 24 hours. And 1 year, we could use the number 365.25 because we have leap years, but just for ease of calculations, we'll just use 365 days. So this next part, I'm going to show the whole class what dimensional analysis is. This is the reason why science works, because units end up canceling, and I'm going to show you how that happens. The only students that need to try this question on the practice booklet are the students taking Chem 20 and Physics 20. This is extremely important for science students going further in Chem and Physics. But if you're taking Science 20, this really isn't necessary to know. There's other ways that you can do this that are a little simpler. So dimensional analysis is a process of setting up fractions, because we know if something is on the top and the bottom of a fraction, it can cancel. Even something like units. So if I put minutes on the top and minutes on the bottom, I can cancel the minutes. So this is going to let me change to any unit that I want just by knowing some of these common facts about time. So we want to change 4 days into seconds. Okay, you start with 4 days, what you have, and this secretly is a fraction. Anything can be over 1 if you want to think about it that way. And I'm going to multiply by a whole bunch of other fractions until all my units cancel and I'm left with what I want. So what I need to do is, if I have days on top, I need to put days on the bottom. What's the next smallest thing that I know about time? Something about a day. One day has 24 hours. What's going to happen to my days? Since they're on top and bottom of a fraction, they're going to cancel, and I'm going to do it again. Hours is on top, so to cancel it, I need to put it on the bottom. What do I know about 1 hour? There's 60 minutes in 1 hour. My hours have now canceled. Cancel the minutes now. What do I know about 1 minute? It has 60 seconds. Cancel the minutes. And the units that I'm in right now are seconds. That's exactly what the question wanted me to go to. So, multiplying fractions. I'm going to take all of the numerators and multiply them. So 4, 24, 60, and 60. Let's multiply all of those. And we get quite a big number. 345,600 seconds are going to go by in 4 days. Now, what would you do if you had numbers that were on the bottom of the fractions? All of our bottoms were 1, so we didn't have to divide by 1. That would be unnecessary. But let's say one of those 60s was in the bottom. You would then divide by 60 because it's in the bottom of a fraction. So just to state this one more time, if you're taking Chem 20 or Physics 20 next year, you need to learn dimensional analysis. There's an example in the practice. If you are not taking those 2 courses, skip this question in the practice. Scientific notation. This is extremely important for students to learn for all sciences moving forward. It's very rare that in something like physics, we'd be working with a nice small number like, I don't know, 17. It just doesn't happen that often because physics studies usually things that are really, really big or really, really small. And chemistry for sure studies things that are really, really small, like electrons and protons. In physics, a lot of what we might study is the radius of Earth, the mass of the sun. These are really big numbers. So instead of trying to write out 24 zeros in a number and risking dropping a zero and having the wrong calculation, we have something called scientific notation so that we don't have to write all the zeros. The way that scientific notation works is you're going to go and find the numbers that aren't zeros. Okay, locate those numbers. You are going to put a decimal in those numbers so that they're between 1 and 10. So I see a 4 and a 5. Where can I put the decimal so that I get a number between 1 and 10? Well, I could put it between the 4 and the 5 and make the number 4.5. Now, obviously, the 4,500,000,000 is not 4.5. Those are not the same number. So what we need to do is we need to say 4.5 times 10. And what does timesing by 10 do? It moves the decimal over. How many times do I want to move the decimal over? Well, I put it right here to make a number between 1 and 10, but it actually lives way down here. So I need to count how many places the decimal needs to move. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I put an exponent on the 10 of 9. The way that we say this is 4.5 times 10 to the 9. Now, with these little red bumps, I'm going between the numbers because that's where a decimal would move to, okay? Now, something to note about calculators, and I'll show you both because in our class we have both the TI and the Casio. On the TI, you're going to put your number 4.5, and then whenever they want to do the times 10 to the power, you're not actually going to hit that. You're going to hit second comma. So above the comma, you can see two little E's. And in your calculator screen, you can see one E pop up. That means scientific notation. All you have to put after that is the exponent. Okay, so those are the same number. On the Casio, this is how it works. 4.5. Your E button is down here beside the decimal, EXP, exponent 9. Okay, that's how you put it in your calculator. Let's try another one. The second one, I found all of the numbers that aren't 0, and I'm going to force a decimal to go right here because that makes the number 3.042. That is a number between 1 and 10. That's what I want. If I put the decimal anywhere else, it's not going to be between 1 and 10. If I put it between the 0 and the 4, it'd be 30. That's not between 1 and 10. So I have to put the decimal wherever it's going to make a number between 1 and 10. Then you always write times 10. And now we count how many places we have to move the decimal to get it where we want. We don't start here and count to where we put it. We start where we put the decimal and we count to where we want it to go. So 1, 2, 3, 4, 5. Now see how those move to the left? That means your exponent is -5. If your exponent is positive, it's going to make a very big number. If your exponent is negative, it's going to make a very small number, like 0.00003042. Now, let's do a note about the calculator notation. So, depending on which calculator you were using, the button either did this or this, okay? Casio and TI. Now, these are solely calculator notations. When your calculator screen said 4.5 E9, that is something that I will never see written on a piece of paper. That is only a calculator notation. That is not proper scientific notation. Proper scientific notation looks like this. You put times 10 to the power of 9. Okay? This little e is just what your calculator does. It's just a calculator shortcut. Okay? So write yourself a note here. Never write the e. It is only a calculator shortcut. or a calculator notation. Okay, so if you were to write a quiz and you wrote your answer as 4.9, 4.5 E9, that would be 100% wrong. That is not correct. You need to write it as 4.5 times 10 to the power of 9. So this last example here, we've got scientific notation and we're multiplying it together. So this is just basically a calculator question. Let's go first on the TI. So you can fast forward a little bit if you have the Casio. On the TI, I'm going to write 3.8 times 10 to the 7. And remember the times 10 part, I don't need to plug that in my calculator. I can, and I can make it work that way, but it's way more calculator buttons. Okay, if we have a shortcut, let's use it. So 3.8 times 10 to the 7 is going to look like this. 3.8. I need my E, so I need to go second comma. Then I put my exponent, which is 7. All right. I want to times this number by 5.4 times 10 to the 10. 5.4, second comma, 10. Okay, so go ahead and write that number down, but remember, don't write it with the E. Okay, so we got 2.052 times 10 to the 18. Let's try on the Casio now. All right. The first one was 3.8 times 10 to the 7. I'll put it in brackets just to show a different way of multiplying. 3.8 times 10 is your exponent button to the 7 times 5.4 exponent button 10. Execute, same answer. 2.052 times 10 to the 18, which written properly does not have an E in it. It has the times 10 part. Okay, that's very important. All right, last little thing that we have to study here, and this does apply in chemistry as well, but we wait to teach you this in physics. First thing we did in chemistry is just tell you how to round. That's very important. If you can't round properly, then on your diploma exam, when you've got questions, if they're rounded wrong, they're just wrong. They don't give you 0.5, they don't give you part marks. They expect that by high school, you're able to round properly. Okay, so significant digits, or some videos on the web will call them significant figures. These are needed in science because all of the numbers we get are usually a measurement. So what happens is, maybe in chemistry, we measure a certain amount of sodium chloride. Our measurement is not perfectly precise. Our measurement can only be as precise as the tool that we're using to measure it. So the last few decimals of a measurement usually aren't exactly right. They're usually rounded off or an approximation. So that means that when we multiply these numbers together, if we get this big long decimal that goes on, we know that all of those numbers are not accurate. So that means that we have a certain rule of how many numbers we can round to. I'm attaching another video that explains this concept extremely well that I need you to watch. Sig digs, significant digits, are in every physics and chemistry course that you take from this point on. You need to know how to work with sig digs. So the rules, any number 1 through 9, before, after, it doesn't matter where that number is, it's significant. If it's an exact value, like I say I have 3 cats, that's not a number, that's a measurement. That's an exact number. It doesn't count for sig digs. Zeros. This is a big list of when zeros are significant and when they are not, but really the only zeros that are not significant are these ones. If they're in front of numbers, they don't count as sigdigs. Okay, these numbers at the back, those count. Zeros in between count, but zeros at the front are not significant. So if I was to sum up this slide with one rule, it would be this. All numbers are significant except leading zeros. And those constants we talked about, like 3 cats. Okay, so all numbers are significant except for leading zeros. Zeros at the front of a number that don't have other numbers around them are not significant. So there's a couple different rules. I'm going to tell you right off the bat. In Science 10, we only use the multiply-divide rule. This is the rule that comes up the most often, so usually it's correct anyways. Adding and subtracting rules don't come into play that often, but when you get to the 30 level, you will need to know this other sig-dig rule. Let me show you it so that you're not surprised in grade 12, but it's really not that complicated. So first of all, let's take this example and let's count the sig-digs. How many sig-digs, significant digits, do you see in the number 5.4? Remember, all numbers are significant except for leading zeros. I see 2 sig-digs in this number. How many sig-digs do you see in 3.24? I see 3 sig-digs. Let's keep practicing. How many sig-digs here? 3. How many here? 4. So all of these numbers were significant because none of them had any zeros at the front. So you just count all the digits. Now, the adding and subtracting rule is a little bit different. You only count the sig-digs after the decimal. So this one would actually have 1 after the decimal and 2 after the decimal. Any sig-dig rule talks about you can only be as accurate as your least accurate number. So the least accurate number we have is the 1 sig-dig. So that means we would write our answer with 1 sig-dig with the multiplication rule. Adding and subtracting is a little bit different. Basically, what you want to do is whatever the smallest number is after the decimal, smallest number of sig-digs, right up here, you're going to round to that, okay? So here's the answer that your calculator would give you. I need to do this to 1 sig-dig after the decimal. So now you use your basic rounding rules from junior high. The 6 rounds the 1 up, so your final answer would be 2.2. So that's just for your information. Don't try and memorize that right now because that won't come into play until at least 30 level or maybe even university. For all of grade 10 and 11, we will only be using the multiply-divide rule. The multiply-divide rule is counting all of the sig-digs in the whole number. It doesn't matter if there's a decimal. And then writing your final answer as the least number of sig-digs. So I write my sig-digs above my values. When you're doing your practice for this unit, every number that shows up, I want you to write the sig-digs of that number above the question. Okay, if you do this for every question in grade 10, you will be really good with sig-digs going into grade 11. So this is what I've done. 3 sig-digs, 4 sig-digs. I'm now going to circle the smallest number. Okay, 3 is smaller than 4. I'm going to write my answer with 3 sig-digs. So here's what the calculator would tell you. See how the calculator gives you all of these decimals? Well, there's no way that whatever I measured up here that was accurate to 2 and 3 decimals could be more accurate than that. That's why we use SIGDIGs. So I need to write this answer with 3 SIGDIGs, but I don't just write the first 3 numbers. I use proper rounding. So when you're rounding, lots of people round incorrectly. Lots of people start at the 9 and round up and keep going. I call those people happy rounders. They are happy to round all day long. They start at the end of their calculator and they round until they get to the spot they want. That is incorrect. I've met students who by grade 12 we discover have been rounding like this their whole lives. Okay, this is incorrect. The only number that matters for rounding is the number right after your SIGDIGs. That 0 is the only one. If it's a 5 or above, round up. If it's not, leave it. So that's why your correct answer is 1.71. The 0 said don't round, so we didn't. Now, I'll introduce vectors and scalars in this lesson, and then the next lesson is to go deeper into calculations with these. So vectors and scalars are any kind of measurements we talk about in physics, one of which does not include direction, and one of which does include direction. So vectors have this little arrow on top of them. It's kind of like an arrow, but you can see I didn't draw the bottom arrow part. Okay? Scalars do not have that little arrow. So if I'm talking about a measurement and I give you direction, and let's say it's 10 meters north, that would be a displacement. That would be a distance that has direction. So I would use the variable d with a vector arrow over it because I said north. If I just tell you 10 meters, that would just be a distance. No direction included, no vector arrow. Okay? Here's an example. When driving in the Indy 500, drivers try to complete 200 laps of the course. If they finish the race, they'll have driven 805 kilometers or 500 miles, hence the name Indy 500. The distance and the displacement are very different. Distance is a scalar, okay? No arrow on top. Displacement, same variable, with a vector arrow because displacement includes direction. So displacement you can think of how far from the start. So since the drivers are going essentially in a big circle, in terms of direction, do they ever go anywhere? Like they put on 805 kilometers, right? But they don't actually get anywhere. They're not 805 kilometers away from where they started. They're still right back where they started. So this is an example of where their displacement, how much space did they displace from where they started? 0 kilometers. But distance, what did they put onto their car? 805 kilometers. Okay, let's try another example. A monkey walks 25 kilometers east and then walks 15 kilometers west. The distance, the scalar that they walk is, they went 25, they went 15, add them together, you get 40 kilometers that these monkeys have walked. What about the displacement? That's a vector. Direction matters. So if they go east and then they go back west, they really don't end up that far away from where they started. Let me do a diagram of this. So north, east, south, west, that's what a compass would look like on a map. These monkeys are going to the east 25 kilometers. Now they're standing right here, okay? They turn around and they walk west 15 kilometers. How far from the start are they? Well, here's where they started, here's where they ended. They're that far west. So how are we going to do this with the math? Well, we can say, see this box at the bottom, that north and east are positive directions, because think about math. Those are the positive axes on a Cartesian plane. South and west are negative directions. So if the 25 kilometers went east, I'm going to put a plus sign on it. If the 15 kilometers went west, I'll put a minus sign on it, and I'll just add them together. What's positive 25 plus negative 15? 25 minus 15, 10 kilometers. We can see from the picture here, east is the direction that they ended up from their starting position. And it looks like that's it for this lesson. So lots of tiny little concepts there for you to work your way through. If you're struggling with them off the bat, don't worry. There's lots of extra practice on the internet that you can find. I'm always available for questions, and we do practice these concepts continually throughout the entire unit. So you don't have to worry if you don't get them right off the bat. You will get them eventually. So do the section 2.1 in the practice booklet and let me know if you need any help.